Okay, in this screen capture, we're going to be looking at the temperature structure bay. Again, this is from the Buzzards Bay section of the Neckoff's mass coastal model, which I just sort of grabbed, again, the Buzzards Bay data. I'm going to, see fake land down here. It's actually the edge of my domain. Let me just zoom this in a little bit. Okay, so this is temperature from the model over the course of the day. This is not subtidal. This is true hourly slices. I took a section across the bay here. Excuse me, give me 2 seconds to make my mouse bigger. And section across the bay. And so again, to orient you, this is a transect. This is looking northeast, so this is the west side of the bay or the south coast. This is the Elizabeth Islands, shallow, deep. This is temperature in Celsius. It doesn't vary much throughout the day, so I will. So we'll look at the. Oops, excuse me. We will look at the time varying component, but it's not as critical as this with temperature as it is with currents. So you see a strong variation from the shallow waters, which are warm, possibly a little too warm, going to deep waters in this 18-degree water, which is essentially what we measured in the with the CTDs. It was 18.5. That's about what we're seeing here. Now let me just first put an up and down slice through there, just a line through from surface to bottom. Oops, something like that, right? Now I don't really have an easy way of turning this sideways, so you have to sort of imagine this is the surface, warmer water 18.4, decreasing to about 18.24 or 2 at depth. So you have a gradient from surface to bottom, a pretty weak gradient. Again, it's a shallow bay, you get a lot of wind. That's not too surprising. And so that's out in the deeper part of the bay, down to about 15 meters. This is roughly where one of our stations was, in that kind of depth of water, in that position in the bay. If I go, I'm going to put a line across, roughly across the surface of the water. If you give me 2 seconds. And so starting from here to the Elizabeth Islands near the surface, you see that the water gets pretty warm here at the coast and decreases rapidly about 19 degrees and then stays in this sort of 18 bolus throughout most of the bay. And let me just start here instead. So you get away from the shallow regions where the water can warm up, and it quickly drops off to the deeper water, which is being exchanged more strongly with Vineyard Sound and Rhode Island Sound, which is colder. So Vineyard Sound down here is colder. Rhode Island Sound is going to be colder than Buzzards Bay this time of year, because we still have enough warmth. In the winter, it's the opposite. But at least now it's warmer in the bay, and you see that it's not monotonic, which actually was a little surprising to me. I think we see that in the observations. I haven't looked that carefully yet, but that between our first and fourth station, the water actually warmed back up. So. Maybe there is something to that. I'm not quite sure the source of that here. I'd have to diagnose that, except that it is getting back to the shallow waters here. In this case, we have, interior of the bay. The deep water is moving up bay because of the northeast wind, and that's bringing in colder water. And perhaps if that mixes near the surface, then that will lead the middle of the bay to be at colder temperatures than the edges of the bay, which are more reflective of conditions in the upper part of the bay, because in the vertical average sense, they're moving with the wind or down bay. So that might explain that. I'm not too sure. As I mentioned before, the holes can have a significant influence on the water in Buzzards Bay, particularly Woods Hole. So you have the colder water coming in Vineyard Sound, and that's mixing around in this upper part of the bay in kind of a complex fashion. One thing I did fail to mention looking at the current slides, if you're talking about a 10 or 20, say a 20 centimeters per second peak tidal current, that is roughly do the math in my head, but I think that's going to come out to about 5 kilometers. So basically you do 2 over pi of that times 2 times 3600 times 6, and that should get you to about 5 kilometers of excursion. So a little drifter in here, and maybe I'll make a run. I'll put some drifters in so we can see how they move around the bay. I will do that, and you'll see that they move generally about a range, something like this. And so you can kind of see that. Maybe I can turn on the temperature contours, but throughout the day you see some fluctuation in the water column here. Here as things tend to ebb out, it tends to warm up. As it flood in, it tends to cool down, but it's not quite that simple. I'm not exactly sure why. I'd have to think about it, not just off the cuff. But if I take if I put a probe in, let's just put it right in the middle of the bay here, this should reflect that. So here's the bay water at that point over the course of the day from midnight to midnight. Again, the cruise was from 8 to 12 roughly. So you can see with this first flood, things cool down. There is cooling down, flooding in, cooling down. And then as they ebb, it starts to warm up, and that makes sense to me because the bay water is generally warmer, and that's fine. But then it's cooling down. No, actually this follows exactly that trajectory, doesn't it? It cools down, then it warms up again. So you see the effects of the tidal cycle there as it moves back and forth, but it's not periodic. It doesn't, return to the same temperature value. So over the course of the day, it's cooling, and I imagine because we have, let's say if we're putting no heat in the bay, we are bringing in this cooler bay water and exporting our warmer surface water in the vertically or in the subtidal sense, and perhaps that would lead to a cooling. Maybe have Miles comment on that. So anyway, that's just thoughts off the cuff. We'll have a look at salinity next. Now temperature, I'll note in the model, tends to be more accurate than salinity because the model assimilates SST. So we have sea surface temperature records from satellites when clouds aren't making the measurements impossible, and those are actually assimilated into the data. We don't force the data to take on these values. In this case, it uses a nudging technique, and Chen, as he developed this model, he played around with that a lot, and what it does now, if I remember correctly, is essentially the model will run for 5 days. It will compute a 5-day sea surface mean at each location. From the satellite, he has a 5-day sea surface mean. Then he goes back and reruns the model, and nudging, basically using an additional term in the model that's proportional to the difference between that 5-day average observation and the 5-day average model to squeeze it towards the real value. So you have some way of maintaining decent surface temperatures, which if in a well mixed situation is going to be reflective of the water column. And again, we're controlling heat flux. Heat flux is strongly controlling the water column as well, and those estimates are coming from the atmospheric model. Salinity, on the other hand, we're putting fresh water into the model, or Chen's putting fresh water into the model, but there isn't a lot of data to assimilate. We have a couple of GOMU stations and things like that, but there are measurements, which we mentioned in one lecture now, of sea surface salinity, but particularly near the coast, they're washed out, and the resolution, and I don't think the temporal resolution is anywhere near the SST, at least not yet. So we were not fortunate to have that. So the fact that we have 18-degree water here and it's going to be close to observation, part of that is because we are assimilating the sea surface temperature here. Without that, eventually the models would diverge from reality, and you'd have to bring them back somehow. These are very complex systems. You don't have, you have errors in numerical methods, you have errors in the bathymetry, you have errors in the model forcings, you have errors in the initial conditions, you have errors in the fact you're using approximate physics, you have errors in the turbulence, and all these things add up. You can't be perfect. Weather models fall apart after 3 days, ocean models will last a bit longer. So what Chen does is he incorporates all sorts of observation data to try to keep this thing constrained and moving in dynamically correct sense. And and essentially never really diverging. So that's pretty impressive. So let's look at salinity next.